Have you ever watched ground crews loading up a plane and thought it's just a big, heavy-duty game of Tetris? Well, it's a whole lot more than that. It's actually a super high-stakes mathematical puzzle. So today, we're going to dive into this hidden world of aircraft optimization. Let's start with a number, 4,000 kilograms. That's 4 metric tons. And that is how much fuel can be saved on a single long-haul flight. So, how do you do it? By shifting the plane's center of gravity less than 75 centimeters. It's a tiny, tiny adjustment with an absolutely massive impact. So, that's the multi-million-dollar question, right? How do you solve this puzzle perfectly every single time a plane takes off? Because it's not just about cramming everything inside. It's about finding that perfect, delicate balance that unlocks major savings and, of course, ensures safety. To really get our heads around the solution, first we've got to understand the problem. And at its heart, it's a fundamental conflict, a real tug of war between two competing goals. See, on one hand, airlines want to load as much cargo and baggage as possible. More weight means more revenue, simple as that. But on the other hand, to save that fuel, you need to get the plane's center of gravity just right, pushing it as far back as is safely possible. These two objectives are constantly pulling against each other. So how on earth do you solve a problem with competing goals like this? Well, you use an incredibly powerful tool called integer linear programming. Now, don't let the name scare you. The best way to think of it is like a special language, a language you use to describe a puzzle and all of its rules to a computer, so it can find the one single best answer. And the absolute hero of this language is something called the binary decision variable. It's a beautifully simple idea. It's basically just a switch that can only be on or off. A yes or a no. A 1 or a 0. That's it. And here's exactly how it works. For every single container, we'll call it I, and for every single available spot on the plane, we'll call that J, the computer asks a simple question. Does container I go into compartment J? If the answer is yes, that little switch, our variable xij, gets set to 1. If the answer is no, it's set to 0. The entire complex loading plan is built from thousands of these dead simple choices. Okay, so the computer has all these little yes or no switches, but you can't just let it start flipping them randomly, right? It needs a rulebook. In the world of math, we call these constraints, and they make sure the final plan is actually safe and physically possible. And these rules are absolutely non-negotiable. First, the final center of gravity has to be within the stable zone. That's a hard limit. Of course, the total weight can't be more than the plane can handle, and you can't overload any one specific cargo hold either. And then, for those big fuel savings, the center of gravity needs to land inside a very specific, very narrow target zone. All of these rules get translated into the mathematical language of constraints. All right, so weight and balance, that's one thing. But what about the actual physical space, the volume? This is where the problem gets really, really tricky because not all containers are perfect little cubes. They have different shapes, different sizes. And this right here is the real kicker. How do you explain a game of Tetris to a computer that only understands simple plus and minus math? How do you tell it, hey, you can fit 2 of these small boxes right here, or you can fit 1 of those big ones, but you can't do both? That either-or logic is a real headache. Let's look at a real-world example from an Airbus A40. A cargo hold isn't just one big empty space. It has specific positions, and depending on how you arrange things, you might be able to fit, say, 6 small containers and 0 large ones, or you could fit 2 small ones and 1 large one. These are mutually exclusive choices, and that's not something simple linear math handles very well. And this is where the solution gets truly brilliant. The researchers came up with this clever trick. They introduced a new set of binary switches. Let's call them the Y variables. Each possible packing layout gets its own Y switch. And the rule is, only one of these switches can be on at a time. So if you flip the switch for the 6 small containers layout, the rules for that layout activate and all the others are turned off. It's a genius way to turn a messy, non-linear spatial puzzle into a clean, solvable set of yes-no choices. So we've got our goals, we've got our basic decision variables, we've got the all-important rulebook, and we've got this super clever trick for handling volume. Let's put it all together and see what the computer spits out. And here is the magic moment. Once you've described the entire puzzle in this special language, a standard, off-the-shelf computer can find the single best answer in less than 10 minutes. And I don't mean just a pretty good answer, I mean the optimal answer. The program tells you precisely which containers to load, exactly where to put them, and even which ones to leave behind to achieve that perfect balance. And hey, don't just take my word for it. This isn't just theory. This chart from the actual research shows that for several real-world test problems, the optimal solution was found in just a handful of minutes, on a regular PC no less. This proves that the method isn't just brilliant, it's practical enough to use in a fast-paced airport environment. So what does all this mean beyond just loading planes? Let's zoom out for a second. This quote from the original paper by Mongeau and Bess really says it all. Their goal was to create a new method that could be solved to optimality, to find that one perfect answer, in a time frame that actually works in the real world. They turned a complex process that often relied on experience and guesswork into a clear, repeatable, and perfect science. The big takeaway here is that this language of optimization is running silently in the background of our lives all the time. It's scheduling delivery trucks, managing power grids, and so much more. So the next time you see a plane being loaded, you'll know it's not just Tetris, it's a perfectly solved mathematical masterpiece. And it makes you wonder, right? What other invisible challenges are being solved all around us right now with this incredible language?